All right, guys, so welcome back. We're going to start off section 4.4 here. And this is going to be pretty short. This cut's going to be short because I'm just taking you far enough to get you to, I mentioned, I think in the last video, the recycled content that I had from last semester. It's basically the same lecture, but you won't have to see my face, right, on those previous videos from the last semester right after COVID-19 broke out. I didn't include my face on any of them. And you'll notice in the next video, which is going to be a continuation of section 4.4, that I'm going to be talking crazy, right? You're going to be like, what's he talking about, man? We're already in the middle of the semester. So just get past that little bit, and then the lecture will resume, and then you'll be good to go. So I'm going to be, still doing everything else. I just won't have to, craft a brand new video from scratch every single time. So that'll be kind of nice. And the material will be there. What I plan on doing to supplement some of that recycled content is if I have the time, I'll throw in some additional examples. Like hop on the whiteboard, talk about coding, that sort of stuff. So I'll supplement a little bit that way. So it won't be just purely recycled content. So just want to let you know, because the way the presentation and the materials being presented is going to look a little different after this video from here on out, all right? All right, so section 4.4 is searching with partial observations. Okay, so what are we talking about? You're talking about a situation where an agent can't really see everything, right? And so what we mean by that is that the percepts that it takes as inputs, they can't tell the agent everything there is to know about the state, right? So in that case, we can say that an environment is partially observable. Now, we're not saying that it can't inform the agent about anything. We're saying that it can't inform everything. That's why the word partially is there. It's partially observable. Okay, and so what this leads to is the fact that an agent could potentially be in more than one state, right? So based on what it knows up to that point, then it can kind of narrow it down, right? It can kind of narrow it down to which state it might actually be in, right? And you take a series of actions, and the agent can determine, well, if I took these actions and they were successful, then there's only so many possible states that I could be in. You don't know for sure, but based off certain actions that the outcomes of those actions can only lead you to one place, right? And so certain actions might lead you to, different places. Okay, you might move right, for example. Well, I'll give you an example, but you might move right in the vacuum world, right? And so, if you move right and that was successful, well, that if it was successful, that you're in the right square now, but that doesn't tell you everything, right? You don't know if the squares are dirty, you don't know if they're clean or not, but you didn't bump into a wall, so you must be in the right square, right? So could be any combination of squares have dirt, right? So whether you're in the right square and there's dirt or not, that's two different possible states that the agent could find itself in, or that you could find yourself in. And so all of the possible states that an agent believes are possible for it to be in, that's referred to as a state space, or excuse me, a belief state space, or a belief states space, or a belief space, right? I'll probably use those terms interchangeably, much to your confusion, and I apologize. The idea is, there's the reality of all the states, but you don't know exactly where you're at. You can only believe where you're at, okay? And so you can use logic to kind of narrow it down. But I could be in state A, I could be in state B, I could be in state C, I could be in state D, based off of what I've done up to this point. I'm not sure yet. I gotta narrow it down. I gotta take some more actions to try to narrow it down. Okay, so a single belief state is one set of physical states the agent thinks it could be in. Okay, now you can have multiple belief states or possible belief states, but one of those is an actual set of physical states that the agent could be in, right? So you've got the physical, you've got reality, and then you've got your perception of reality. Okay, so in reality, the agent is in a state space somewhere. It's in a state somewhere. Okay, that vacuum is in the left square or it's in the right square, but it might not know 100% for sure, right? And so all of the states that it thinks it could be in, that is a belief state. Okay, so another type of problem is a problem where the agent just is completely and utterly blind, right? The percepts give you no information, or gives the agent no information. Now you might think, well, then how is an agent going to function in that environment if it can't see anything, right? Well, this is an example of a sensorless, also known as conformant problem, but agents can actually still do stuff, and they can actually be useful with the stuff that they're doing, even if they can't perceive the environment. As a matter of fact, there are certain types of activities where it's more efficient for an agent to ignore its environment, to not be able, well, I say ignore, I mean not sense its environment, okay? Because there is a cost. You have to pay for sensing, right? There's all the overhead of, running the cameras, translating the images into something that the agent understands, and so on, right? So depending on how you construct an algorithm that causes the agent to perform a series of actions, right, you can get the agent into a particular goal state no matter where you started from, and disregarding the fact that you can't sense the world that you're in. Okay, so by setting the logic up cleverly, you can guarantee that you end up with the agent getting into a state that you want it to get into. Okay, so consider sensorless vacuum world. Okay, you could have a situation where the vacuum agent can't perceive anything about its environment, right? So when it first starts off, the agent could be in any one of these states, doesn't know, right? So its initial belief state would include all 8 states, okay? Its initial belief state would include all 8 states because it doesn't know which one it's in, okay? It can't sense anything, right? But let us say that the agent decided to move to the right, okay? Well, if it moves to the right and it doesn't bump into a wall, then logically, there's only 4 possible states that it could be in. Isn't that right? Because that would have meant that you went from left to right without hitting a wall. So if you don't hit a wall, after you complete that right action, I mean, even if you do hit the right wall, even if you do hit a wall, right, you know that you must be in one of these states, 2, 4, 6, or 8. So you've just shrunk your belief state, okay? So the entire belief state space would include the 8 possible states you started in. That would be one belief state. And then you tried to move right, and the result of that, whether you hit a wall or not, would be another belief state where there's only 4 physical states, 4 actual states in that belief state, okay? And so, if you do that, move right, and then you do the suck action, right? Now, whether the floor is dirty or not, because remember, you can't sense it, okay? Whether the floor is dirty or not, okay, you're going to end up, assuming that this is a reliable deterministic action, which it is, okay, for this example, you're going to end up in a right square that's clean, right? So you're moving into yet another belief state. Now, what possible states can have the agent in the right square, in the right squares clean? Take a look at figure 4.9. It's going to be either 4 or 8. That's it. 4 or 8. That's all you got, right? Because you moved to the right and then you sucked, right? So once you suck, the dirt's gone. So there's only 2 logical possibilities. Okay, you're at the right, in the right square, and you're in a clean square. So if you want to make sure that you end up with a clean floor, from there you just dial in, move left, and then suck, right? So when you do that, that guarantees that the agent is going to get you into state 7. right? When you're done, you're going to be in state 7. You're going to have a clean floor. It's logically impossible for that not to be the case, right? So here we have, granted it's a toy problem, but an example of an agent that can't perceive its world at all and still hit its goal state, right? Just by using a little bit of logic here, okay? So, that process, there's a term that the text uses for it, coercing, or you can say that the agent has coerced the world to state 7. Okay, so here's the key, right? So you can't do, you're not going to do a search on the physical states, right? In the states in reality, you can't, okay? Because you don't know what state you're in when you first start off, right? And as the search progresses, that tree is not going to necessarily match reality because you don't know what your initial state actually is, okay? So what you do instead is it's the space of belief states that gets searched, okay? Because you know what you believe, right? Where you could be, right? I'm the vacuum. I think that I'm in any of these 8 states, right? So you can run an algorithm on that because you know what the states are and you know that you believe, that you're in one of those states. It doesn't matter what you can actually observe in the real world. You can search through your own mind, right? Even if you can't observe the world, you can still think about the world, okay? Now, any existing solution is a sequence of actions, okay? Now, the percepts are always going to be empty because you can't perceive the world. So what does that mean? 100% predictable, right? So if you think that you're in a particular set of states and then you run a series of searches from each one of those individual states, you can have your search proceed deterministically because you know what you're thinking about where you're at, okay? So you're just thinking in your mind, okay, I'm going to go through, if I'm in this state, then I can take all these actions, and then you can form a tree there that's 100% reliable. Because the fact that you don't get any percepts at all means it's 100% predictable that you're not going to observe the real world, right? So this isn't like, previous examples we discussed where, we have to do an and/or graph, or an and/or search. Because what happens if we think we tried to move to the right, but we actually ended up in the left? No, when you're thinking in your head, right, those are your thoughts. You're thinking about your own belief state, okay, or your own belief state space. So even if you do have a non-deterministic environment, you don't need to have an and/or search, okay? There's no contingencies here because you're thinking through the solution in your own mind, in your own beliefs. Okay. So let me talk to you about some of the pieces of this. So what you've got is basically duplicate functions, right? So we've been talking about the actions function, results function, goal test, a step cost function. Okay, so what happens is that you still define the underlying physical problem, right? And so then you have the versions of the functions that would work on the physical problem if it was fully observable. Okay, and so the text refers to them as action sub P, result sub P, goal test sub P, step cost sub P. So you're going to be doing things in your mind, right? You're going to be doing things, executing searches on the belief states, okay? And that's going to be built on top of the actual physical states, okay? You'll do searches in the belief states and then you'll try to run your solutions against the physical states and try to coerce your goal state. Okay, so belief states, that's a possible set of physical states. So if you have n states for P, okay, now one belief state is going to be one set of physical states. When you first start off, vacuum world, okay, your belief state, okay, is going to equal all of the physical states, right, all 8 of them, okay, so you don't know why? Because you don't know where the agent is starting, right? It's not like the previous problems we were talking about where you were given as part of the problem definition, your initial state. You don't know what it is because you're blind, right? The agent's blind. It can't sense anything about the world. It can't tell, okay? So what actions should the agent take? Okay, you know, if you're thinking in your mind, right, in your belief state, you're like, okay, I have 8 possible locations I could be at on the vacuum. Okay, I got 8 possible states I could be at. Okay, what are all the possible actions I can take here? Well, it depends, right? Um, some actions are going to give you safe moves, right? Moves that are legal, okay? And so some aren't, right? So, for example, if the vacuum is in the right square, okay, and and you want to move right, okay, should you move right? Would right be a valid action, right? Or would it be a legal action? Okay. Well, there's going to be a wall there. And so maybe you leave that one out. Okay. Or if you had some kind of state, a set of states in your belief state where you had one state where legal moves were to move north and south, and you had another state, physical state, in your belief state where the only legal moves were east, west, or north, right? So if you have a situation like that, what you're doing is you're getting an intersection of all the safe actions. So your search in your belief state space would proceed with only the north action, because the north action, the go north action, is common to both of them, okay? Because, you know, in the state over here, we were only able to go north and south. In the state over here, which would be part of our belief state, we were able to go only north, west, and east. There was no valid south, right? So you only go with the ones that you have in common. Okay, that's safe to do because if you're in either one of those states, you can move north from either one of them. Okay, and that will lead you somewhere. That'll enable you to cut down your belief state. Okay, into a smaller belief state. Okay, so the transition model. Oh, almost forgot. If all the moves are safe, if all the actions are safe, let's say that you were in 2 different states, and you know, for both states, you could move north and south. Okay, well then all of those actions could then be applied in your search, right? Because if you were in this state or you were in this state, moving north from either one is valid, right? You can transition to a valid state. Or moving south from either one is valid. You can transition to a valid state. Okay, so that becomes a union, right? So that's a union of all of the belief state actions that can allow for safe, legal moves, right? But if there's multiple states in your belief state where that's not the case, then it's an intersection. Okay, so the transition model. Okay, what you're trying to do is you're trying to generate that new belief state. You know, for the vacuum world, you're trying to go from 8 states down to 4. Okay, so that step, the text refers to as the prediction step. Okay, so the agent isn't going to know, you know, which state in the belief state is the actual correct one, right? So when we were in vacuum world and we had 8 initial states, physical states in our startup, in our first belief state, you know, we're going to predict where you might end up. Okay, so you know, if you take a right action, we're predicting that we ended up in a state space, a belief state that had 4 physical states in it. Okay, that's the prediction step. Now, which one did you actually end up in? Don't know, right? You'd have to continue on. Okay, so for deterministic actions, okay, the set that can be reached is determined by, here's some math for you. Basically, all this is saying is if it's deterministic, then you can count on how your belief state is going to change, right? Because there's no possibility of, you know, staying in a place, or maybe ending up in 3 different locations instead of 1. You know, remember when we were talking about deterministic versus non-deterministic in the and/or search, right? So, you know, you're going to get a new belief state that's going to be the result of taking the actual results of the physical state, had you apply the action to all the possible states that you could be in. Okay? And for non-deterministic actions, you have to further take into consideration all of the random states that you could enter into. I'm going to show you a graph here in just a second. But it sounds maybe more complicated than it is. Or maybe I could have been a little bit more clear on the explanation. Basically, all this is saying is that, look, if it's deterministic, you've got a one-to-one transition from one belief state to another belief state within the belief state space. Okay, if it's non-deterministic, it's one-to-many. So take a look at figure 4.13. So what's labeled A here, on the left, you've got one belief state, and you go through the prediction step. You're trying to transition into a new belief state. Okay, so the agent's thinking, all right, here's where I could be. I could be in state 1 or I could be in state 3. All right, so according to what's possible in the real world, that's where those functions with sub p would come in, right? You would take each state in your belief state and feed it through those functions to determine, well, what are the legal actions, right, in the real world, in the physical world, in the physical states. What are the actions that I could do? Okay, and since it's deterministic, you'd say, okay, well, if I was in state 1 and then in the real world, in the physical world, in the physical states, I took a right action, well then in the real world I'd end up at state 2, right? Similarly, if I think in my current belief state I could be in 1 or 3, then according to the physical model, I could take a right action from 3 and I'd end up in state 4. So the right circle here represents your new updated belief state, right? Because if you were in the left side, you thought you were in the left square, and in either one of these two states, you weren't sure if both squares were dirty or just the one you were in were dirty. If you took a right action, and you can because in the physical states you could, in the physical world you could, then you just apply that right action to both of them, and that makes your new updated belief state. So your updated belief state, you don't believe you're in this left circle anymore, you think you're in the right circle now because you moved right successfully. So you're either in state 2 or state 4. Okay? Because that would be the result of applying those actions in the physical world. Okay? Whereas B, this is, non-deterministic. This is be the result of your belief states changing when there's a chance that the action you take doesn't take, right? So remember with the slippery vacuum world, there was a chance that you didn't move at all, right? So if your current belief state is, well, I think I'm in state 1 or state 3. Now, if I move to the right from state 1, one of two things is going to happen. I'm either going to move or I'm not, because remember, in that slippery version, could be the case that the vacuum doesn't move at all. So if I try to move, I'm either going to not move at all, or I'm going to end up in that right square. Similarly for state 3. If I try to move to the right, I will either move there or I won't. So what you can see is that when you have a non-deterministic model, right, your state space, your belief state space, your belief state, right, gets bigger. Okay, the overall belief state space gets bigger because you go from 2 to 4 in this case. It's a union of all possible results that could happen. Whereas here it was a one-to-one mapping. Here it's one-to-many. Okay, so hopefully I explained that okay. Hopefully that makes sense. Okay, now goal test. How do you know how can you tell that you found what you're looking for, that you found a solution? Okay, a particular belief state, the set of all physical states that you think you could be in, that's going to satisfy the goal test only if all of those states in your belief state, which are states that correspond to the real world, if in the physical real world, every one of those states in your belief state was a goal, then you're gonna pass, right? Then you've reached the goal. So in other words, if where I think I could be as an agent okay, I believe I'm in squares 1, 2, 3, and 4. I believe I'm in state A, B, C, D. Okay? You run your physical goal test function on all of the states in your belief state. Is this a goal? Is this a goal? Is this a goal? Is this all 4 of them are goal? Okay, pass. Goal test. Right? Logically, I must be in one of my goal states if they pass. If every state that I think I could be in passes the actual physical state goal test, then I must be in a goal state. Okay? Right. So path cost depends, right? And so the textbook says, hey, for right now, just assume that each transition you make, right, the cost of moving each action is going to be the same, just to make it easier for right now. Okay, so let me walk you through figure 4.14 to give you an idea, okay, of how this works. And I think there's only a couple more things I have to say about this. Then we'll put a cut in, and then I'll hand you over to my recycled content. Okay. So figure 4.14. Okay. So check out this big box right here. Right. So this entire thing represents a complete belief state space. Okay. But this is one of the belief states in the belief state space. So this right here is where we're starting out from. Okay. So the agent starts off. You just powered it on. You hit the power button on the vacuum cleaner. Wakes up, okay, and it's like, I can't see anything. I'm blind. I can't perceive anything. Can't hear. I can't detect that there's dirt. Nothing. Okay. Now you know something about the world. You know the world you're in. You know the physical world, the properties of the physical world. You just don't know what state in the physical world you actually are in. You don't know what actual physical state you're in as the agent, but you know in your mind, I must be one of these 8. That's my belief state. I believe I'm in one of these 8 physical states. Okay? So then you could run the actions P, right? You take that actions function that's defined for all the states in the physical world, right? In the real world, for all the physical states. And then you just apply that to all of the states in your belief state. And that's going to tell you what the legal actions are. So you would apply that to state 1, right? And that would say, okay, well, you can go right. You'd apply that to state 7. Well, you can go right. You could apply that to 5. Okay, well, you can go right. You can apply that to 3. Okay, you can go right. Okay? And so now you're doing your prediction step. Okay, well, if I go to the right, I'll transition into this belief state, right? Where you end up going to either state 2, 4, 6, or 8. Notice there's all the different configurations of dirt on the floor. But you definitely have, because the action was right. The dirt situation didn't change, but you now believe that you're in the right square because you applied right to all of the possible states that you could apply right to. Okay, so this is one belief state. If you can successfully move to the right, then the vacuum's in the right square. Dirt be damned. And then similarly for going left. Okay. Now, if you're in this belief state and you're going to go through and do your prediction step again, well, what if I go left? Okay. Well, if I go left, then it ends up being in the same state space as if I had gone left originally. So that's what this arrow means here. Now, what if you start off in your initial state space here and you do the sucking action? Well, you either have dirt on the floor or you don't, right? So, you feed that into your actions, your physical actions function, and say, okay, well, if I'm in state 1, what would be the result? Can I legally suck here? Yeah, I can. Okay, and then the physical results function would say, all right, well, then you would end up, in this state 5 here, right? And then you do the same thing. Well, what if I do a suck? Can I do a suck on 2? Yeah, you can. Well, then that would lead you to state 4, and so the belief state would shrink, right? So every single time you go through this, when it's deterministic, your state space is shrinking. Okay. Now, from going from right to suck, we just cut it in half again, didn't we? Right? Because if this is your agent's current belief state, it says, okay, well, what are the possible states I can suck in? I can suck in 2 and 6, or Nevada from the Raiders, 2 or 6, although they won today, so I shouldn't talk trash. And so, what am I predicting will be the outcome, right? Well, what's my results? function in the physical for physical states. Well, I'd apply that to 2 and 6, and that would lead me to a state space that's half the size, because it would guarantee, upon successful completion of that action, that both the right squares got nothing in them. Now that doesn't say anything about the left square situation, dirt or not. Okay. Now from that state space, do it again and go through your prediction step. What are the legal actions? Well, the legal actions are left. I can't suck. So if I go left from either of those states in the real world, then that would lead me to believe that I'm in one of these two states here. Right? Now, from one of these two states here, what are the possible legal actions I could take? Well, I could suck if I'm on a dirty square. So what would be the result of me being on a dirty square and doing a suck? Well, that would move me into state 7. Okay. So here I'm either on a clean square or I'm on a dirty square. So if I do a suck, that's going to guarantee that I'm on a clean square. Okay. So every single time you do an action, it makes your belief state get smaller, because you're learning a little bit about the world. Even if it's implicit, right? Because if you originally could be inside of 8 states, you don't know if you're on the left or on the right, and you can legally move right, and then you predict, well, if I move right, here's what's going to happen. Then you must be in one of those right squares. Okay, see how that game's played? Okay, so we can come up with a complete formulation of this belief state problem. Okay, where we're trying to think about, okay, well, how does the belief state work, and how do we transition all that? Once we've done that, then any of those chapter 3 search algorithms, they're going to work, right? Because you can do the searches on your belief state for reasons I already kind of talked about. Okay. All right. Now, because of that, because of this idea, you can do sensorless problem solving. Okay, it is possible, it is theoretically possible, but it's rarely feasible in practical terms. Okay, so we talked about, I think in chapter 1, talking a little bit about the history, and they were like, okay, here's all these things that we can do, but there were physical limitations. Why? The size of each belief state, and therefore the overall belief state space, can be huge. Okay, so for example, if you had a vacuum world that had the possibility of having an initial physical state of 10 by 10 squares instead of 2, right? That would mean that belief state space, or that belief state, excuse me, would have 100 times 2 to the 100th power physical states in it. That'd be ginormous. Let me say that again, right? So let's say that vacuum world, you can have initial state that's 10 squares by 10 squares. Think of all the combinations of dirt that could be in all those squares, where the actual vacuum is. Think about all of that. It means that initial belief state would be 100 times 2 to the 100th physical states, right? Because of all the different combinations of dirt in squares, no dirt in squares, agent here, agent not there, vacuum in square this, or it could be over in this one. You don't know where you're at. The vacuum could be in any one of those 100 squares, and any one of those 100 squares could be dirty or clean. Okay, so what can be done about that? A better description, all right? And that's going to go towards go to knowledge representation, which we're going to talk about in chapter 7. So what you can do to try to make it a little bit more efficient, okay, is you don't have to search through every single possible physical state. Okay, so what do we mean by that? Okay, once you have your initial belief state, okay, this right here, you can then run any of those search algorithms that we studied on chapter 3, or in chapter 3, using any one of these states as the start state, okay, the initial state. And then you just run the algorithm just like normal, okay? And then once the algorithm comes back successful, then you can just say, okay, let's do it. You can carry out the actions blind, okay? Now, that would require you to, potentially run an algorithm on every single one of these initial states. Okay, so that may be wasteful. Okay, so what you might do is a compromise is to build up the solution, one physical state at a time. So what you do is you find a solution for state 1, starting off from state 1. Does it work for state 2? That solution also? Yeah? Okay, cool. Go and see if it'll also work for initial state of state 3, because you would go through and you'd play out all the actions. But if it doesn't, then go back and find another solution for state 1. So you're basically just saying, okay, I got a solution for state 1. Does it work for state 2? No. Okay, well, let me see if I can find a different solution for state 1. And then you can just do this one at a time, right? Until you got a solution that's guaranteed to work for, all 8 initial states, right? All right. Now, there are some things that are impossible without sensing. So, it sounds good, but it's not always possible. So, a sensorless 8 puzzle problem, for example, that's impossible. But if you let the agent be able to sense just one tile, what number is in one tile, you can kind of brute force it and it becomes possible. It's not very efficient, but it's possible. All right, so what about partially observable problems? So what we just talked about was we talked about problems where you can't see anything, okay? And we're almost finished with this, and then we'll have a cut here, and then I'm turning you over to the recycled content, okay? So for when you have partially observable problems, you have to say, okay, well, how does an agent utilize its percepts, okay? How do those percepts sense the environment? How does that work? Okay, so for example, maybe the vacuum can sense its position. Maybe it can sense if the position's dirty, but nothing else, or maybe both, right? But nothing else. So what you have is you have a percept function where you pass it a state, and what it'll do is it'll return a percept for some given state, right? So here's what you could perceive. Now, if it's non-deterministic, then you're going to get back, a set of percepts, okay? So here's all the possible things that you could perceive. Okay, so a couple of details here. When you have a fully observable problem, by default, that percept function, right? It's you've got one percept for a state, and so you're gonna perceive your own state. You have no problem understanding or knowing what state you're actually in. Now, a sensorless problem, where you can't sense anything, where you're operating blind, like we just described. Well, then if you feed S to that percept function, then what you're going to get back is nothing. You perceive nothing. So a fully observable problem, the state that you perceive, the percept, is just the state itself. But if you can't perceive anything, then it's null. You don't know anything. Okay, that percept function is going to give you null. Okay, so here's the thing with partial observations, and why this is a big deal, because you're looking at that, you're like, so what? Duh, right? But here's the thing. If you only have partial observations, it could be the case that multiple states could give you the same percept, right? So, for example, if this is your percept, I'm in, maybe space A, square A, and it's dirty, okay, as opposed to square B. Well, that could come from state 1 and state 3, right? So let's say you can perceive what square you're in, and whether or not it's dirty. So let's take a look at our belief state here, right? Which states could you be in if you perceive yourself as being in A and it's dirty? You could be in 3, or you could be in 1, right? So in that case, by that definition, that percept function would give you the set of percepts that indicate to you that, hey, look, you can be perceiving state 1 and state 3 here, right? Both of those match. Okay. Okay. Okay, so in this case, when we're dealing with partial observations, you got the actions function, you got the step cost function, you got the goal test function, and just like how they were based on the physical problems, that underlying physical problem when it was completely sensorless, same thing. Okay, but transitions have to take place. You know, your prediction a little bit more complex. Okay, so when you're trying to transition from one belief state to another, as you're moving through or searching through the belief state space, you got three steps. You got prediction, observation prediction, and update. Okay, and so now, dear viewer, dear reader, this is where I'm gonna pass you off, hand you off to my recycled content from the previous semester. So this is as far as we had gotten in regular lecture back in March, and from there I continued the lecture virtually, just like we've been doing all semester. So that's it for me. So that's the last cut. From here on out, you'll be able to finish off chapter 4 through the videos already have posted. Now you'll notice something in the recycled videos. Okay, the next video is going to start off kind of weird, me referring to what I'm going to do. Again, that's from March. Okay, but another thing too that you're gonna see is that the slides in the videos after this, some of the text is red, some of it's crossed out. That's because those were updates. Those were edits I made for clarity for the class, and I hadn't updated them for you yet. So the slides that you have posted on Blackboard right now just took out all those edits, right? The crossed out stuff is deleted. You know, stuff that's red is now black. So you got the new and improved version of the slides, you know, revision 7, I think, you know, with some of the mistakes taken out that I noticed in the previous lectures. Okay, so if you have any questions on that, hopefully it's not too confusing. Hopefully you'll be able to see what I mean. But if it is, give me a holler, and you know, I'll get you straight. I'll get you squared away. All right. Cool. Okay, so that's that then. We'll see you in the next video, and you won't have to look at my face anymore. So win for you.